That's taking a picture. Okay, good. So here we have some ammonia mixed with vinegar and cabbage juice as an indicator. And this is an acid-base reaction that reaches equilibrium. These two test tubes have different amounts, but they are at the same temperature, pressure, conditions, so they're going to have the same equilibrium amount of reactants and products. And now we're going to put one in cold water and one in hot water and shift the equilibrium. Now you guys know that equilibrium is affected by temperature based on whether a reaction is endothermic or exothermic. So what do you all think about this acid-base reaction? What have you learned about acid-base reactions? Can you guess if we're endo or exothermic?
We should let it sit on the table.
Yeah.
Or my page. Don't eat my page.
Anyone want to
Please
guess
don't.
endothermic or
I
exothermic?
like my page.
You
like your page too.
Acid-base tend to exo.
Yes, they do. Acid-base reactions just tend to be
I like my thumb
exothermic.
more though. Please eat the page.
I like
Don't eat my
Micah's
thumb.
wording. He doesn't say they're always this or that, but acid-base reactions in our experience have always been, and certainly tend to be, is more than allowed, exothermic. So when we write this reaction, will we put energy on the reactant side or product side?
It's kind of aching. That's a bad sign, I think.
Products.
Yep. So this reaction gives off energy as a product. So we're going to write
Probably nothing.
on the product side. Where is my equation? Okay. So everyone try to write a balanced equation while not letting your test tubes tip over.
Or what?
For ammonia plus,
Are these both liquids or
Vinegar.
they are?
so they're both aqueous.
Probably my thumb isn't supposed to be like
If your
aching.
thumb hurts, you're welcome to go wash.
Probably it's not supposed
Or you could
to
just
ache.
put vinegar on yourself. Neutralize that. All right,
I guess
so vinegar.
Pass the vinegar. I will try.
It's acetic acid, correct?
It is.
I will pour vinegar on myself.
And of course, this is an equilibrium, so we are going to write it with a double arrow. Jolene has a lovely,
Vinegar is
she's tested the
usually-
pH of her lab sheet. It's neutral.
We tested my thumb and stuff.
All right, so remembering that ammonia is a covalent base, even though vinegar behaves like it's ionic. Whenever you have
Hopefully
one
that
or
works.
the other is covalent, you're going
If
to
not,
make.
my thumb will be gone.
Well, normally you would if both. Yeah, if we had like sodium
This isn't doing
hydroxide and
anything.
vinegar, we would make a salt and water.
There's
But in this case, we're going to
something.
make two ions because ammonia is covalent. So, what two ions do we think about here? Micah?
We would have acetate,
Is it getting
acetate
darker?
ion.
and then we would have
I don't
ammonia.
think so.
If I'm not mistaken.
Yep. The acetate ion and the
Plus
ammonia
enthalpy.
ion.
Yes.
Yes,
When nothing
and
happens.
Micah already told us that energy is a product because it's exothermic, like most acid-base reactions. So we'll put energy on that side. Okay. So then I'm going to tell you that the product side tends to be greener in color when the cabbage juice is used as an indicator. The indicator is not part of the reaction, so you don't need to worry about the cabbage juice. The reactant side tends to be bluer. So that will give you kind of an idea of which way the reaction is shifting based on adding energy or removing energy, whether in ice water or hot water. So, and of course, greener with cabbage juice means more basic, just so you know. A bluer is closer to purple, closer to neutral. So, take a guess before we pull them out and compare.
Bluer is neutral.
Purple's neutral, bluer is closer to neutral. Maybe more like a pH of 8 or 9 instead
So it
of
would be less
10 or
basic.
11. Less basic, more neutral. Greener is more basic. So, the hot water, for example, when we're adding energy, Right, or adding energy, which way do you think it'll shift?
Toward the reactant.
Toward the reactant. So the one in hot water should be
Blue.
bluer. So now
It is
each
kind of bluer.
group of 4 should compare. The hot water should get bluer.
There's definitely.
It is a little.
Yours is definitely.
Yeah.
Like, yours is definitely. Yeah, ours is definitely. I think it was bluer anyway, but it's bluer more noticeable. Yeah, it's noticeable. Plus, it was already an isotype when we compared to before, so it's maybe bluer.
Any luck, guys? Oh, theirs really worked. So look at this.
I think there's
Put-
bluer to begin with.
Hey, ruin the fun. So this one on the, I can't tell my left from my right. The blue one was in hot water, and the green one was in cold water. So, I mean, but they were not nearly that different before, were they? I mean that. So now that you've seen that, reverse them, because equilibrium, right? So put the hot one in cold and the cold one in hot, and see if you get a color change that way. So let's compare. Yeah. All right, so the cold one is somewhat darker. I definitely couldn't call that one based on greener or bluer. Yes, but don't switch because we're not really seeing a lot of evidence with yours yet. At least we're seeing one, but no, not that. I can't aim.
Switching our tubes, we don't need to write that down.
Not yet, no. Hopefully we'll get to switch your tubes. Poor Austin. I can't get the test tube in the shot. Yeah. So you guys can write that you switched them. Some of you may have to write the other group switched them once we saw something happen. Just gonna spread the heat around. So we want adding energy shifts it this way. The hot one should be bluer. That's what we're saying. Yes. Where is the water? I'm going to add a little bit of water to everyone's ice solution just because I don't know that we're getting good contact with the ice without some water in there. Hopefully, is everyone's hot water still fairly hot? Yeah, pretty hot. Okay. So let's look at the lab questions briefly while things kind of come to temperature a little bit. So on the lab help sheet, what we see is it says, make sure you write down observations about the color of the test tube and ice water at room temperature. Oh, we didn't keep one at room temperature. Well, you guys saw them at room temperature. Hopefully you kind of observed, and in hot water. The reaction is exothermic. Cabbage juice will indicate that the pH is higher or more basic when it is green, and the pH is lower, but still basic, closer to neutral when it is blue. Write a balanced chemical equation for the equilibrium, indicating whether energy is a product or reactant. So we have that. That'll go in your data section. Is the reactant side or product side more basic? How do you know? The green one is more basic, so that's the product side. Describe how the equilibrium shifts with temperature changes. So in your discussion, that's really kind of the meat and potatoes of the discussion here. That you want the, you want to talk about how adding energy will shift the equilibrium, how removing energy with the ice will shift the equilibrium. Make sure you mention Le Chatelier principle, you know, like the important concept that we're examining here. You probably want to define that in a good discussion. If you want to try to force this reaction to completion all the way to the product side, would you use hot water or cold water? Anyone want to take a guess at that?
Cold water, correct?
Cold water.
Because we're removing energy and thus to relieve stress, more reactions have to get.
So if you cover that, then you're pretty good. And while we're waiting, let's go for an objective and a conclusion. Now that you've kind of seen what happens, what do you think the goal was here?
Something to do with observing chemical equilibrium and how temperature affects, temperature stresses the reaction and the effects of that stress being relieved. Or using Le Chatelier's principle in action.
Yes, your objective could mention Le Chatelier's principle. It could mention the effect of temperature and equilibrium. There are plenty of ways you could do that differently, but that's one example. And how about a conclusion? Well, we can't make a conclusion yet because we haven't observed. So everyone observe. Hopefully what do you think? Cold should be bluer or greener?
Should be greener.
Cold should be greener. Is that what we're seeing?
Yeah, slightly. We should have brought the NXT color sensor.
Do you want to?
image.
Yes. I actually probably have a spectrometer in my bag at the moment, but so this is cold right now. All right,
You want me to get more ice?
No, I think we're pretty well done. Oh, look, there's really worked. Can you aim the camera this way, please?
Well, no, the one in hot water wouldn't do it.
It would just be more blue.
And it didn't go back.
Adding energy shifts to bluer.
I think it got greener than it was. Like, it got
That's
darker.
nice of you.
It really did. It was really cool. And that one definitely got darker.
Well, maybe it will. They were different shapes. Don't film this. It's terrible.
When it's colder, it'd be greener.
All right, let's think it through one time.
I did. I got the wrong thing.
Maybe we're saying the wrong thing. It could happen. All right, so Erin, can you balance this so I don't spill it everywhere? Thank you. Okay, so let's think through. The cold one, in the cold one, we're removing energy. And when you start to remove something, you make more of it. So the cold one should be greener. Is that what we've been saying?
Yeah. Okay, there you go.
Okay, the cold one should be greener. The cold one should be greener. So hopefully, maybe we'll see something going on. What are you guys seeing? Ours is really nice. The cold one should be greener.
I think it just looks dark.
That's actually pretty cool.
This usually works with no hitches, no problem. I don't know. The cold one should be green. I'm really hoping that this one is going to do something, because at least they're doing something. Let's see. I'm going to get this one. The cold one should be greener. So, just to submerge more, I'm going to.
But they
Alright.
lived theirs already. Oh.
Alrighties. This is empty, and we'll just see. We'll wait. We'll go over some stuff, and we'll look again.
We should be ready for that observation. right?
Yes. And we'll write another observation at the end of class. How much longer do we have?
Ours didn't really do anything. So
We have about 20 minutes.
Okay,
22
let's
minutes.
look at a few acid or base ionization reactions. And then hopefully your conclusion ideally would be adding energy shifts to the reactant, removing energy shifts to the product.
What about the procedure? Are you done with the procedure?
Hopefully, I mean, it's not very much of a
All,
procedure.
all I have is we put the ammonia in until it was green, and we didn't.
And then put it in hot and ice water.
Okay.
All right, let's see. I've got a list of things we should look at for acid-base ionization. And we'll look at some of them. Oh, and one thing I want to tell you about your homework next week. So Dr. Weil gives you this giant list of rules for figuring out oxidation and reduction and the numbers involved for each thing. And they're really complicated, and you can go through his whole little process, but essentially if you just assume that everything kind of ionizes, and maybe we'll look at one of these in terms of what you're going to do next week. If you just look at the charge on each ion, that really works out oxidation reduction wise almost every time. So his complicated rules can be seriously simplified. So don't panic when you read through 16 and you're like, this is a lot. It's really pretty easy if you just kind of consider ion by ion instead of element by element. All right, so
Could you say that again?
I know since you haven't read Module 16, it would be really hard. I'll see if I can kind of show you on one of these.
Are we reading all of chapter 16?
All of 16 this week. We're going to shorten our year by 1 week because we have so many snow days. So let's look at, if he said write the KB for ammonia, since we're doing ammonia right now, and ammonia is aqueous, not AG. So ammonia is aqueous. If you're going to write the KB for ammonia, what would you do? So is ammonia going to ionize? Yes.
If you add water.
Okay, why would you add water?
Well, first of all, NH3 by itself is not an ion. You have to add water to make it ammonium,
Right.
which would make it an ion, and then you have hydroxide, so therefore you would have two
You won't
ions.
have a hydroxide. Oh yeah, you will have a hydroxide once you add water. So getting a hydroxide is going to require water. And also NH3, I mean, both of these are nonmetals, functionally anyway. And so this is covalent. So when you have a covalent, you can't ionize it without adding the water. So you're going to have to add water to something like ammonia because this is covalent. You can't ionize a covalent without some other thing to react it with. So like Micah just said, that's going to make 2 ions. The water will act as an acid because we've defined this as the base. It'll donate a proton. You'll make 2 ions that you know about. And then both of those ions will be aqueous because they're ions. So then you'll write your KB with your product concentrations over just the one reactant concentration because that's a liquid. Try to zoom through a bunch of these. How about KB for sodium hydroxide? Well, do we need to add water or can we ionize this?
We can ionize that.
Yep, this is ionic. So you don't need to add water. You just form its 2 ions. And it's simple. Then you do, all 3 are aqueous, so you just do products over reactants for the KB. We used vinegar today. So we'll try acetic acid, which of course Dr. Wow would always write, like, so I don't want you to be fooled. Would you need to add water or not add water for this? No, because really what this is this, and it acts like an ion. So you can just ionize that into 2 familiar ions and be done with it. These are definitely similar to things that you're going to see. Here is maybe the evilest of them that you might see something like on the test. What is that thing? So anytime you have a nitrogen-like compound, yeah, he's gonna, I hope he tells you aqueous, but anytime you have something that has this N in it, whether it's ammonia or some other compound with an N, you're probably looking at a covalent base, okay? So he'll probably define it as a base. He'll say, write the KB for this. So you're going to know it's a base. So when something's a base, what does it want to get? It wants to get a proton, right? So when you have a covalent acid or base, in this case a covalent base, you're going to have to add water. And this is one you might want to write down and get familiar with. But you have to add water for covalent bases, whether it's something familiar like ammonia, something less familiar, but still nitrogen bearing. Of course, if you look at your periodic table, things that are similar in chemistry to nitrogen, things like phosphorus, in that same period with the same periodic properties, phosphorus, pH3, NH5P, those things would behave very similarly and would be covalent bases. So if I did this, what do you think I'd make?
HCH5.
So if a base wants to get a proton, I'd have CH6N. And then it would get one H plus, so it would form that. Another key point you want to see is that if this side contains two neutral compounds, the net charge on the other side needs to be neutral. So if you have a 1 plus and a 1 minus, they would cancel their charges, and you'd end up with neutral on this side and neutral on that side. If you don't end up with both sides having equal charge, you've got a problem. Really? If it's covalent. Nitrogen and phosphorus are kind of dead giveaways. In terms of acids, there aren't like loads of covalent acids running around. Really, I mean, if he told you to write the Ka for water, since water is amphiprotic, you could, but you can't add water because it is what it is. So I guess, I don't know, I can't think off the top of my head of a covalent acid. Well, I can think of one, but it's a horrible molecule. I don't know if I could write it from memory. It's a big molecule. I don't think of a covalent acid. Do I have a list of other tricky things? Maybe. Here's one more. Yeah. Alright, BF3. Is it ionic or covalent? That's kind of the first place you want to look.
It's ionic. No, yeah, it's ionic because of boron.
Is it? I almost have to look.
Good check.
I wonder if he actually does this. So, boron is listed as a non-metal.
Okay, so this is a covalent then.
So if it was
Very-
ionic, you would just split it into two.
Two ions and let it go, but boron's listed as a non-metal. So this is going to be covalent. Make sure you have your periodic table, of course. So since it's covalent, we're going to do this. And it's going to tell you, well, that's just an equilibrium. It's going to tell you, that's kind of evil. I don't see how you can do this yourself. I'll write it for you. This, I don't think this is on the test. And in fact, now that I'm nervous, I'm just going to look at the test one last time. And what is it going to make?
So it's double replacement? Or something like that?
Something like that. What does it make? Oh, it's going to make boric acid. Look again. Yep. Boric acid. You guys use that to kill pests around the house, maybe? Boric acid. Yeah, so you would have to then balance that, which, while I peek at the test to make sure I've sort of showed you everything that could be thrown at you, you can see if you can manage to balance that. That is not, I think, on the test. I don't know why it's in my notes. Was it like a practice problem or something? That could be. It gives you all of those.
How did you come up with that?
I know how I came up with that. Okay, so an acid plus a base gives you, well, an acid plus not exactly a base gives you a salt plus water. So it's a similar sort of reaction. That's not on the test. What is on the test? That. Yeah. So This one's not that important, and even if you didn't balance it, I actually don't want to waste a minute on that because it's not there. This is very important for the test. Remembering that nitrogen and phosphorus are very similar compounds, and this one. Nope. Well, this one is balanced, right? Yes. So do we remember this? Is this the perchlorate ion or something?
I think that was also another extra thing that you never told us to memorize.
Yeah, I've erased the one evil one because you don't need to worry about it. But I am going to worry about this. This is literally on the test, and I'm literally going to tell you what it is because it's not something that it's the chlorite ion. So if you're given this and you're told to find the Ka for this, what would you do with that?
Well, instinct tells us to remove the H so you have an H plus ion and the ClO2 negative ion.
So you're like, okay, I can form two ions. And these are two that I know, even though we haven't used this chlorite ion since module 9, I don't think at all. So then you would just put products over reactant and they would all be aqueous. You would be done with that. And that is really the last evil problem on the test.
Why is that one evil?
Well, it really isn't. It's just widely missed because it's not an ion that's familiar, and people are like, I'm supposed to make familiar ions. So I'm showing you personally the chlorite ion is a real ion that really you can make.
Sorry, I probably would have done like hydrogen oxide and
Yes, don't split up the chlorite ion. It's a real polyatomic ion. And review the polyatomic ions.
And they're all
Ionization. Review the polyatomic. There's one more acid ionization on this test that is similar. You're just breaking up an acid into ions. And it should be two more familiar ions than that. Very similar. I won't write the Ka because I know you guys can do that. But these two reactions are things you really want to know for the test.
You would figure it out eventually.
All right, so let's go back to our lab and think. Do we have